Transit photometry. Transit photometry can be seen as a very smart use of eclipses. When a planet passes in front of its star, it will cover it slightly, causing it to dim its light for the duration of the transit. If these drops in brightness happen periodically, you probably found yourself a planet. As you can imagine, the luminosity variations are incredibly tiny. The conditions need to be perfectly right to detect these infinitesimal changes. To detect anything, in fact, the exoplanet's orbit and the line of sight of the observer on Earth must be very close to each other. The probability of this happening is very small, and it becomes smaller the further away the planet is from its host star. Gravitational microlensing. When all the methods have failed to work, scientists look for yet another interesting phenomenon: the peculiar effect the gravitational field of a massive object has on light. To understand this, we need to jump back in time to when relativity was just being discovered. When studying general relativity, Einstein predicted that massive objects bend space, which will cause the attractive effects we experience every day. Gravitational microlensing relies on the idea that its relativistic effect will make the gravitational field of an object act like a lens. Given two stars, almost exactly aligned, the incoming light from the background star is bent and magnified by the gravitational field of the foreground star. If the star has a planet orbiting around it, then the planet will offer a detectable contribution to the lensing effect. This method is extremely sensitive to the passage of a planet and can detect bodies that are much farther away than all the other methods. The biggest downside is that this kind of measurements require perfect alignment between the background star, the foreground star, and the Earth, which is an occurrence that can only happen once for a system, and it only lasts days or weeks.